So this is section 2.3, the national zeros theorem. Okay, so objective for this section is number one, number of the zero given polynomial function, and rational zero theorem. So this is actually the very important, and this the course rule for the sign, and then boundariness theorems. Okay. So number of the zero for the polynomial function. So let's recall the two main topics of this chapter thus far. Topic one is in section 2.1, we found the zeros polynomial function that were already factored and will be factored using technique from the earlier algebra course. Topic 2, in section 2.2, we could factor polynomial function by performing division as long as we were told some of the factors. So example from the 2.1, p of x was 3x cubed minus 6x squared minus 12x plus 24 can be factored as 3 times, so 3 is a GCF. So pull it out, and then if you factor by grouping, and then you will get this, which means we get the two, actually the zero. One is a 2 from this linear factor, and then we got negative 2 from this linear factor, okay? And then the 102 is a multiplicity of 2, and then the other negative 2 is a multiplicity 1. So therefore, the counting multiplicity p of x is a 3 zeros, even though you see only 2 zeros. And then match the degree of the polynomial, which is 3. Example from the 2.2 was f of x equal to 6x to 4 minus 5x cubed minus 23x squared minus 7x plus 5. It was a factor as the 2 times of this form. So we got 1, 0, negative 1 is a multiplicity of 2 from here. And then 5 over 2, and then multiplicity 1. And then 1/3 is going to be the multiplicity 1. Therefore, the counting multiplicity, f of x has a 4 zeros, okay, totally. Alrighty, so let's look at the next page. So considering these two examples, we notice that the degree of the function is the same as the number of the zeros. So that's very important. So the degree of the zero is the same number as a zero. Degree of the function is a degree. Degree matched to the and the number of the zeros. This is no coincidence, okay? In general, any polynomial function with degree n greater or equal to 1 would have exactly n0 provided each zero is counted using as a multiplicity. So if you consider the process we used to factor using synthetic division, this should not come as a surprise. Consider any polynomial with a degree n. Each time we found the remainder of 0, we were able to factor the polynomial into the linear factor of the degree 1, and a second factor that is a degree 1 less than the polynomial being divided. If we are able to continue this process until there are only linear factors, there will be n linear factors, will be result in n zeros counting the multiplicity. So with the knowledge of the how many zero counting multiplicities that a given polynomial must have, we now continue with the topic of the factoring polynomial function by division. The slight change from the last section will be that none of the factor will be given in the questions. So to introduce the added dimensions to the factoring process, we are going to consider polynomial function side by side in its factored and unfactored form. So let's say we have a factor form here. And then we multiply this together to get this product, which is we keep the 2x plus 1, 2x minus 1 from the previous ones. And then you are distribute the 2x to the 6x squared to the negative x and negative 15, and negative 1 multiplied by 6x squared, negative x and negative 15. And then you got this product. So once you got, and then we just combine like terms together. So once you've done that, and then the above the process of multiplication shows that this is actually the same as this, which is to find the zero of the set is set the f of x equal to 0, and then you get the 0. One of the 0 is 1 over 2, and the other 0 is negative 3 over 2, and then because you set each linear factor equal to 0, and then one of the 0 is going to be 5/3. So if you have a the general forms of the polynomial, we get the 0 of the 1/2, negative 3/2, and 5/3. So let's consider separately the numerator and denominator of the three zeros. The three numerators are, as you notice here, was 1, 3, and 5, okay? And also, so notice that these numbers are the all factors of the 15, which is, you get the 15 from here. So whatever you see the number from the numerator is a factors of 15. And also, the constant terms of the function is 12x cubed minus 8x squared minus 29x plus 15. First, we must look at the original multiplication to see the constant 15 came from the product of all of the constant terms of three linear factors. Secondly, we must realize that when solving for zeros, the numerator of each zero comes from the constant term in each linear factors. In general, numerator of every rational zero of the polynomial function must be a factor of the constant term of the function. Likewise, we're going to have a 3 denominator, which is 2, 2, and 3, right? So 2, 2, 3 here, which means when you look at the leading coefficient, right, which is 12, so 2, 2, 3 is also the factors of that, okay? So like looking at the original multiplication, we'll see that the leading coefficient of 12 came from the product of all the leading coefficient of the three linear factors. So we must also realize the denominator of each zero comes from the leading coefficient in each linear factors. So in general, denominator of every rational zero of the polynomial function must be a factor of the leading coefficient of the function. So we just look at what zero should be available for the polynomial to look at it as a numerator and the denominator as a product, okay? Let's look at the next page. So all of this summarized in the following theorem. So we call the rational zero theorem. So if we have a polynomial function as a general form, with it has to be the integer coefficient, which means a sub n minus 1, a sub 1, and a sub 0 must be the integers, okay? So no fraction, no decimal. And then, of course, first term should not be the 0. And then the constant term is a sub 0. And then any rational 0 of the f of x be in the form of the p of q. And then where the p is the factor of the constant a sub 0. And then q is the factor of the leading coefficient a sub n. So in order to get the rational 0, the rational zeros, and then we'll get this form. Okay, I think I changed it. It should be the ZT, okay? Rational zero theorem. So we will use this theorem to create a list of the rational numbers that have the chance of being rational zero for the given polynomial functions. So we're going to use the rational zero theorem to create the list of all the rational number that might be a rational zero later, okay? So let's say rational zero theorem is about the p over q. Then p is going to be the plus minus of, you need to put all the factors of a sub 0 and then factor of a sub n. So which means plus minus factor of a sub 0 is a 10 here, and then factor of a sub n is 3 here. So now I'm going to write down all the factors of 10, which is 1, 2, 5, and 10. And then factors 3 is a 1 and 3. Okay, and then you just need to put that as the ratio, okay? So plus minus, and then take the 1 over 1, which is 1. 1. And then take the 2 over 1, so 2. Now take the next number 5. 5 over 1, 5. 10 over 1, 10. And also, take the 3 as from the 1, so 1 and 3. So plus minus 1/3, plus minus 2/3, plus minus 5/3, and plus minus 10/3. So whatever solution you'll get for that polynomial function as a 3, as a rational, you'll be the one of those, okay? Number 2, use the rational zero theorem to create the list of all the rational number, maybe the rational 0 for the f of x equal to x to the 4. So since it's degree of 4, you get the 4 possible zeros, okay? So in order to get the rational zero theorem for the P over Q, which is plus minus of factors of a sub 0, which is 12, and then also factor of the a sub n2, okay? So factor of the 12 is, so this is how you put it. 12 is 1 times 12, 2 times 6, 3 times 4. So there's a 6 of them, okay? So 1 and 2 and 3 and 4 and, yeah, plus minus later. And 6 and 12. And then 2 also has a 1 and, I already put the plus minus, right? So I have 1 and 2. So now put the ratio as, I take the 1 from the denominator, put all the numerator, so 1 and 2 and 3, 4, 6, and 12. And then take the 2 from the denominator, so 1 over 2. 2 over 2 is same as a 1, so take the 3 over 2. 4 over 2 same as a 2, and 6 over 2 same as a 3, and then 12 over 2 is the same as a 6, okay? So this is the rational zeros, a possible rational zero, okay? Alrighty, now that we can create the list of the possible rational zeros, we factor polynomials by the finding enough numbers in the list that give you the remainder of the zero. Okay, so now we have 3x cubed minus 2x squared plus 23x plus 10. Actually, define all the zero here, okay? So first of all, we already talked about this as a rational zero theorem, which is a plus minus of factor of a sub 0, 10, and then factor of a sub n, which is factor of, oh no, sorry. We're going to put the auto factor for the 10. So which is 1, 2, 5, and 10. And then factor of the a sub n, which is a 3 here, which is 1 and 3. So you'll get that as 1 and 2, 5, and 10. And then 1/3 and 2/3. And 5/3, and then 10/3. Okay, so those are the zeros we might get, okay? All right, so let's try. Now we have to test them out. So I'm going to use starting from the 1, okay? So I got 3, negative 20, 23, and 10, and then divide by 1. So drop the 3 using the synthetic, okay? And then 3 times 1 is 3, negative 17, and then negative 17, which is a 6. 6 times 1 is a 6, and 16, which is not equal to 0. So 1 is not going to be the 0, which is x minus 1 is not going to be the factor. Now try it again. 3, negative 20, 23, and 10. And then I use a negative 1. So drop the 3. 1 times negative 1, negative 3, negative 23. Positive 23, which is 46, minus 46 is going to be negative 36, which is not equal to 0. So negative 1 is also not going to be the 0, which means x plus 1 is not going to be the factor. Now I want to go to 2, say 3, negative 20, 23, and 10, and then I'll divide by 2. So 3, 6, negative 14, negative 28, negative 5, and negative 10. Yay, we got the 0, okay? Which means now the 2 is a 0, okay? Which means x minus 2 is a factor. Now, we have a polynomial function, which was 3x cubed minus 20x squared plus 23x plus 10, and then now it becomes x minus 2 of, and then we are using this form as a quadratic, so 3x squared minus 14x minus 5. So it becomes 3x squared minus 14x minus 5. And then I noticed that the 3x squared minus 14x minus 5 is factorable. And then you get the 3x and x. And then I need to get 14 as a difference. So I should put negative 5 here and then plus 1 in here. Yeah, so this is a complete factor form. Okay, alrighty. Okay, let's do the next problem. So on the next problem, so rational zero theorem, so plus minus of factors of a sub 0, which is 12, and then factor of 2. So we got factor of 12 is 1, 2, 3, 4, 6, and 12. That's a lot. And then 2 else is 1 and 2. So if you put it out as, it's going to be plus minus 1, plus minus 2, 3, 4, 6, and 12. Also 1 over 2, and then 3 over 2. Okay. Alright, so try this. So starting from the coefficient, it is a synthetic division. Then I'm going to start with the 1. Drop the 2, multiply 2 times 1 is 2, subtract negative 1. Negative 1, negative 25, negative 25, negative 12, negative 12. Yay, we already got a 0. But the problem is, now we have 2, so x minus 1 is a factor. Is one of the factor, but we only got one factor so far. So what I do from the 2, negative 1, negative 25, and negative 12, and then so this becomes 2x cubed, because start from the x to 4, right? Minus 1x squared minus 25x minus 12, okay? But still it's a 4 term, but you can do as a factor by grouping. So I'm gonna starting over. So I got 2, negative 1, negative 25, and negative 12. But as you noticed, though, you might have a 0 as a multiplicity of 2 or 3. So I'm going to try 1 again. So don't go back to the 2, negative 3, negative 24, 13, and 12, okay? You can just use whatever the bottom row that you can use, okay? So drop the 2. 2 times 1 is 2, 1. And 2, negative 23, negative 23, which is negative 30. Oh, sorry. What am I doing? Yeah, I messed up. Sorry about that. So 1 times 1 is 1, negative 24, negative 24, negative 36, which is not going to be a 0. So only the 1 is a 0, okay? So there's a 1. 1 is a multiplicity 1. Now I'm going to do it again with the 2, negative 1, negative 25, and negative 12. And then I'm going to use negative 1. So negative 1, drop the 2, negative 2, negative 3, 3, negative 22, and 22, and 10, which is not 0. So negative 1, I'm not going to use that. So it's not going to be a 0. Now start it over. 2, negative 1, negative 25, negative 12. And then now you can use 2. But 2 is not going to work. Okay, so if you're going to continue, I want to actually... the one that I want to use is, I'm going to use a negative 1 over 2. What about it? Negative 1 over 2, okay? You can use a fraction too, okay? So the negative 1 over 2 is one of the possible rational zeros. So drop the 2. 2 times negative 1/2 is negative 1, negative 2. That's a 1, negative 24, which is 24. Yay, we got 0, isn't it? That means this is also the 0 too. So we got 2 zeros so far. So which means now we have your function is x minus 1, x plus 1/2. And then you got 2x squared minus 2x minus 24. So now we have a 2 linear factor and 1 quadratic factor. But 1 quadratic factor, I think this still might be factorable. So what I do is, I'm going to factor the 2 from the quadratic factor. And then I get x squared minus x minus 12. And then I can just, it's a quadratic, so yeah, so I can put that as x minus 4 times x plus 3. Yeah, so these are the factors. So which means you can still use a negative 3 too, or 4. Okay? Alright, so that's, so now we got 4 zeros so far. Alrighty. Let's move on to the another rules. Okay, so the next one is about the Descartes rules of the signs. So when we're looking back at example 2, we had 16 different numbers in the list of the possible rational zero. It took the 7 different division to factor the function down to at the most quadratic factors. The Descartes rule of the sign will give a way to sometimes shorten the list of the rational number that may be the rational zero of the given polynomial function. So the Descartes rule means if the function is a polynomial function with the terms of the descending order and the real coefficient, and then we can actually find out how many numbers of the positive real zero from the f of x using the number of the sign change. And then or less than number of the from the positive even integer, okay? So, and then for the number of the negative real zero, we are using f of negative x to find that as number of the sign of the change. And then it's going to be less than the positive even integer. So in order to determine the number of the sign changes, a polynomial function must be written in descending order, and we consider the signs from the one coefficients to the next. Determine the number of the sign change in f of x. Okay, so sign change means you need to look it up the all terms. So this is a one term, another term, another terms, and another term. Okay, so take the sign with it. And then when you look at the first to the second, that was a positive, or this is a negative, isn't it? So this has a sign change. So check. But from here to here, it's negative to negative, which means there's no sign change. And then the third one is the negative to positive, which is what? Yeah, there is a sign change because of positive, right? So sign change. So this time, you can say that there's a number of the sign change is going to be a 2. And then you also need to get the less than this number by the positive integer. So you need to go down by 2, which is a 0. So so that's we call the sign number of the sign change. Okay, so let's look it up, the problem we have here. Okay, so example 4. Use the Descartes rules of the sign to determine the number of the possible positive zero for f of x. So we are looking for the number of the possible positive zero, okay? So we are using the original function, okay? So this is, yes, there is a sign change because of positive to the negative. And then this to this is a negative to positive, yes. This is a positive, positive, no. Positive, negative, yes. So this time is you get the 3, but you need to actually the decreasing by 2. So next number subtract 2 from the 3 is a 1. So it's gonna be the, so this means that you might have a 3 or 1 possible positive real zero, which means it could be the 3 positive real zero or 1 positive real zero. If you say, oh, I might get 2, no, that's not possible. I might get none, that's not possible either. So at least you can get the positive real zero from here. But the real zero means it contains rational and also irrational. Now the next problem, I'm looking for the number of the possible negative zero. So in order to get a negative, I have to use a negative x. So if you plug it in negative number for the x, yeah, that's how you write it. And then of course we gotta simplify. But the good thing is when you have even power, negatives go away, right? So this is same as 3x to 4. But when you have odd power 3 with the negatives, negative stays. So negative times negative is a positive. And the 11x cubed. Even power stays. The negative go away. And then positive negatives and negative 5x minus 12. So in order to find the change of the sign, is only this is a change of sign. So it happens once, isn't it? So this is going to be a 1. So that means you got only one possible, the negative, the real zero this time, okay? Alright, so why does the Descartes rule of the sign include a phrase or is less than the number of the by positive integer? Recall that all the non-real or complex zero come into the pair. And these numbers are the neither positive or nor negative, which means because it's complex numbers, so we don't need a positive or negative, okay? But it always comes with a pair. So let's say you have a 3 positive real zero. which and then the if you have a 1 negative real 0, but this is a degree of 4, right? So order to be a number of the 0 must be equal to 4. So total must be a 4. So yeah, 3 plus 1. So that case, there's non-complex 0 because 3 plus 1 already makes a 4. Let's say there's a 1 real 0, positive real 0, and the 1 negative real 0, which means you still need a 2 more, right? That 2 comes from the complex 0, so total equal to 4. Okay, so no matter what you get, you should get the same number of the degree, which is the same. That's going to be the number of the zeros. Okay, so number 6. Describe the possible cases for the 0 of the g of x, and then 8x cubed plus 7x squared minus 3x minus 20. So total 0 you'll get from that function is going to be 3. So let's get the number of positive real 0. So only the change is this one, right? So that's a 1. And then I need to find the number of negative real zeros. So which means I have to use a g of negative x. So if when you have odd power, it changes sign. So 8 is a positive, become negative 8x cubed. Next one is a square, so the stays the same. And there is also power 1, change the sign, and then minus 20. So if you see that change of sign from each term is 1 and 2, right? So there's a 2 or 0. So the positive real 0 is going to be a 1 and 1. And then the negative real 0 going to be a 2 over 0. And then total 0 going to be a 3, so which means there's none for the complex 0. On the second case, it's going to be the 2 for the complex 0 because 1 plus 0 plus 2 equal to 3. So how can Descartes' rule of the sign be helpful when factoring a polynomial function by division? So factor f of x equal to x cubed plus 4x squared plus 11x plus 14, and determine that it's a 0. So let's try the problem that we can apply what we learned. Okay. All right. So first of all, I need to find the rational 0 theorem, which is plus minus factors of 14 a sub 0, and then we put the factors 1. So this is only going to be 1, 2, 7, and 14. I think that's all, right? So starting it. So 1, 4, 11, 14. So if I use but this time actually there'll be a no positive real 0 because there's no sign of the change, right? So which means there's no possible positive real 0, okay? So if I put the f of negative x, I got negative x cubed plus 4x squared minus 11x plus 14. So I see that there's a 2, okay? So I'm only going to test them at the negative number. So drop the 1, negative 1, 3, negative 3, which is 8, negative 8, which is a 6, which is not going to be a 0. So negative 1 is not going to be 1, 4, 11, 14. Next negative number is negative 4. Drop 1, negative 4, 0, 0, 11, negative. Oh. Okay. And then negative 44, which is a negative 30, right? Which is not going to be a 0. But I skip 1. So 1, 4, 11, 14. I use the negative 2, okay? So drop 1, negative 2, 2, negative 4, which is a 7, 14, negative. It's going to be 0. Yes, we got it, right? So this is a 0. So for the 0 is this, and then you got x squared plus 2x plus 7. So set equal to 0, which is not factorable, so you have to use a quadratic formula, right? So if you do the quadratic formula, it will be the negative b plus minus b squared minus 4 times a times c over 2a. A is a 1, right? Sorry about that. And then when you simplify it, I get the negative 2 plus minus radical 24 over 2, which is Negative 2 plus minus 2 radical 6i over 2. And then simplify as a negative 1 plus minus radical 6i, okay? Yeah, so you got the 2 complex 0 and then 1 real 0. So zeros are x equal to negative 2, the multiplicity of 1, x equal to negative 1 plus 6i, radical 6i, and multiplicity 1, and then x equal to negative 1 minus 6, radical 6i is a multiplicity 1, 2. So those are the three zeros you can find from the Q function, which is matched to degree of k. Alright? So in general, if the polynomial function has no change in the sign, there will be a there can be a, hold on a second. Okay, so x, okay, so there'll be, it can be a no positive real zero, okay? So no positive real zero. So, but you might get the negative zero, okay? So we have to kind of change it here. Sorry about that. There'll be a no positive real zero, okay? Alright, so let's look at the next page. So example 8, to factor g of x equal to 2x cubed minus 9x squared plus 18x minus 27 and determine the 0. So I want to find the possible rational 0, which is going to be the plus minus factors of 27. Don't worry about negative 27. It's going to be plus minus anyway. And then factors of 2, which is 27 has 1, 3, 9, and is it 27, right? And then plus minus 1. No, we already have plus minus here. 1 and then 2. So in order to find that, you get the plus minus 1, 3, 9, 27. And then 1/2, 3 over 2, 9 over 2, and 27 over 2. So yeah, so there's nothing repeated, okay? Alrighty. But this time, actually, there's a change of sign is 1 and 2 and 3. Oh, so definitely there is a possible positive real 0 as a 3 and 1, 3 or 1, okay? So I'm going to use the positive number first, okay? So I have 2, negative 9, 18, and negative 27. And then I'll divide by, sorry about that. We'll divide by the 1. So we're going to use a positive, okay? So there's a 3 possible or 1 possible positive reals here. Drop 2, 2, negative 7, negative 7, 11, negative 11, a positive 11. It's going to be negative 16, which is not going to be a 0, which is 1, it's not going to be a 0. So let's try it again. So next number is going to be a 3. Drop to 6, negative 3, negative 9, and 9, 26. Yay, we got 0, right? So 3 is a 0. So now we have 2x squared minus 3x plus 9, which means you can just set equal to 0. And then if it's a factorable, you just can factor. If not, you can use a quadratic formula. 2, right? So, but 2 times 9 is 18. Sum of it is not possible, okay? So we have to use a quadratic formula. So negative b plus minus b squared minus 4 times 8 times c over 2 times a, which is 3 plus minus 9 minus 72 over 4, which is 3 plus minus radical negative 68 over 4. What am I doing? I don't think it's right, okay? So the 9 minus 72, I don't think it is here. So 9 minus 72, it's going to be 63. What am I saying? Sorry about that. Oop. Okay. Yeah, so I got is 3 plus minus. So 63 is 9 times 7. So 3, I read 7 over 4. and then which is not reducible. Okay, so that's it. So you get so zeros are x equal to 3, which is a multiplicity, everything is a multiplicity 1, and then x equal to 3 plus 3 I raised 7 over 4, which is a multiplicity 1, and then x equal to 3 minus 3I radical 7 over 4, which is a multiplicity 1 too. Okay, so those are the zeros. So in general, if the polynomial function has all of the coefficient of the term with the odd degree on one side and all the other terms has a coefficient with the opposite sign, the Descartes' rule of the sign guarantee that there will be a no negative real zero. Alrighty, so let's go up to the next page. So the final topic of this section is a boundedness theorem. We give a secondary way to sometimes shorten the list of the rational numbers that may be the rational zero of the given polynomial function. So unlike the Descartes rules of the sign, the boundedness theorem may be shortened the list after every single synthetic division is performed. So boundedness of the ness theorem. So if the function be a polynomial of the degree n greater or equal to 1, with the coefficient n divided by x minus c. So if the c is greater than 0, every number on the bottom row during the synthetic division is non-negative. So all comes out positive or 0. And then we can call the c is the upper bound, which is there's no 0 that greater than that. Now the c is a negative number. The number of the bottom row during the synthetic division alternate in sign, with the 0 being considered as a positive or negative as needed, and then we call the c is a lower bound of the real 0. Okay, for the real 0. Okay, so consider. So we have f of x q plus 10x minus a. So the possible rational 0, which is going to be the rational 0 theorem, plus minus factors of 8 and then factor of 1. So which is we got 1, 2, 4, and 8. Okay, so let's find out the upper bound. Okay, so you got 1, but this is the same as x cubed plus 0x squared plus 10x plus minus 8, isn't it? So 0, 10, and negative 8, and then divide by 1. So there's a drop 1 and 1, 1, 1, 11, and 11, and then 3. Okay. So remainder is not 0. So x1 is not going to be the 0. Okay. And also x minus 1 is not going to be a factor. But the good thing is, this is actually do you see that it's all positive numbers? That means 1 is the upper bound. So we don't have to try the 2, 4, 8 as a positive. Okay. Now go to the low bound 1, 0, 10, and negative 8, and then I'll start with the negative 1. So do that. So 1, negative 1, negative 1, 1, 11, and negative 11, negative 19. So as you notice, this is the signs of what? Alternating way. Signs are alternating way. That means negative 1 is the lower bound. Which means we don't need to test out the negative 2, negative 4, and negative 8, which means your 0 will be between this, okay? So this time, that's the only thing. So at this point, we have to check the 2 number, eliminate all the 8 numbers from the list generated by the rational 0 theorem. Okay, so yeah, so which is this one doesn't have might not have any of the zeros. Okay, so for the real 0. All right, so we can now summarize the process of for factoring and finding a 0 of the polynomial function as follows. So number 1, create a list of the possible rational 0 using the rational 0 theorem. Number 2, consider the Descartes rules of signs to see if the list can be shortened. And number 3, begin division, checking if the boundedness theorem can be eliminate more numbers from the least after each completed division. Number 4, factor down to at most the quadratic factors. Number 5, solve for the 0 using the zero product property and using the quadratic formula as needed. Okay. Alright, so let's do the example 10. Okay. So we have a f of x equal to 4x cubed plus 16x squared plus 11x minus 10 and determine that it's a 0, okay? So find the possible rational zeros from the rational zero theorem. And then I got plus minus factor of 10 over plus minus factor of 4. So which means we get 1, 2, 5, and 10. And then 1 and, oh, we already have plus minus, right? So it's going to be 1 and 2 and 4. So in order to find the possible zeros are plus minus 1, 2, 5, and 10. And then 1 half, 5 over 2, 1/4, and then 5 over 4th. Okay, so those are the possible zeros, okay? It's a 4. So let's starting to here, okay? So 4, 16, 11, and negative 10. So starting from the 1. So drop the 4 for 20, 20, 31, 30, and 21. Not going to be a 0. So 1 is not going to be the 0. 4, 16, 11, and negative 10. And then I'm going to use a negative 1. And then 4, negative 4, 12, negative 12, negative 1, and 1, negative 9, which is not going to be the 0. So negative 1 is also not going to be a 0. 4, 16, 11, negative 10. And then let's try the 2, which is 4, 8, 24, okay, 48, and 59. Twice that is 118. Which is going to be 108, which is not going to be the 0, so 2 is not. 4, 6, 11, and negative 10. Hopefully you can find soon, which is negative 2. Drop the 4, negative 8, negative 2, 4. Oh, 16, sorry about that. I know there's mistakes I made, okay? Alright, so drop the 4. Sorry about that. So negative 8 and 8. Negative 16, negative 5, and 10. Oh, yeah. Well, now we got 0, isn't it? So this is a 0. So now, which means this becomes 4x cubed plus square 8x minus 5 equal to 0. Okay. And then this is also factorable too, which is we get that as, that's a good thing, okay? So 2x plus 5 and then 2x minus 1. So the zeros are x equal to negative 2 and negative 5 over 2 and then 1 over 2, which is, you can see that those are zeros from here, okay? And then with all the multiplicity, we won this time, okay? Okay, let's I think that's all for this section. So this section is kind of heavy, but I talk about a lot of stuff, okay? All right, thank you for listening.